In chapter 5, we're going to take a look at probability. So first we have to talk about randomness, probability, and simulation. So there's something called the law of large numbers that says if you observe more and more repetitions. Oh, I just spelled repetitions wrong. Of any chance process, the proportion of times that a specific outcome occurs approaches a single value. The most common example would be you flipping a coin here. If I flip a coin 100 times, the proportion of heads is going to approach 50%. Heads is going to come up about 50% of time. Now, this is not to be confused with the law of averages, which says that probabilities have to average out. So if you flipped a coin 4 times in a row and gotten heads, the law of averages would say, well, I'm due to get tails, so the next time should be tails. That's not what the law of large numbers says. Each flip of a coin is independent, which we'll talk about later, of any previous flip. So each time I flip a coin, there's a 50% chance it'll land on heads and tails, heads or tails. It doesn't tell me what the next flip should be. So probability is a number between 0 and 1 that describes the portion of times the outcome would occur in a very long series of repetitions. So again, the probability of flipping a coin and having it land on heads is 1/2, because if you repeat flipping a coin a very long amount of times, 1 out of the 2 flips has to be heads or tails. So that leads us into the next thing. So what happens when we flip coins in the short run and in the long run? So I'm not going to actually flip a coin, but you can do this on your own. So when you flip a coin, each time you flip it, you can land on heads or tails. So I can flip a coin and it can land on tails. And then I can flip it and it can land on heads. Then I can flip it again and it can land on heads. Then it could land on heads again. Then it could land on tails. Then it can land on heads. So just in a short period of time, more of your outcomes could be specifically heads or tails. So in here, I flipped a coin 6 times and 4 of the outcomes were heads while only 2 were tails. That doesn't mean that there's a bigger probability of flipping heads or tails, because there was only a short amount of flips. But if I were to flip a coin 50 times, while there might be more heads or tails, they should be roughly the same in 50 flips versus in only 6. So next we're going to talk about how we come across finding behavior and finding probabilities, and it's through something called a simulation. So it's an imitation of chance behavior based on a model that accurately reflects the situation. So we could run a simulation of flipping coins 100 times to show that the probability of landing on heads or tails is 1/2. So what we do in a simulation is we typically use random digits to imitate chance behavior. So it is better to obtain random digits from a table or some type of computer software because it's faster and it's easier than doing all of the math to complete the probability calculations for a probability model. So the nice thing is you can simulate many repetitions with a computer instead of doing it by hand. But you have to be careful to set up the appropriate probability model, and the random numbers must be independent. So that's something we're going to take a look at more in depth later in a different section, but it just means that every time the probability is the same instead of changing. So when we perform a simulation, we have to state the question of interest. So we have to say, what are we trying to do here? We then have to write a plan which describes how we're going to use a chance device to imitate one repetition, and then explain how we're going to clearly identify the outcomes. And then we're going to actually perform many repetitions of our one simulation. And lastly, we can conclude and use our results of our simulation to answer the question of interest. So it's like a mini little scientific process. So if we look at an example, at a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery at a school assembly. The 2 lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by a student council member for the college credit statistics class. When both golden tickets went to members of that same class, some people thought that the lottery had been rigged. There are 28 students in the college credit statistics class, all of whom are eligible to park on campus. Design and carry out a simulation to decide whether it's possible that the lottery was carried out fairly. So we have to start with our state. Like, what are we planning on doing? So our question is asking, is the lottery fair? Okay. Next, we have to plan how we're going to carry this out. So I would assign the students in stats the numbers 0, 1 to 28, and we can use this function on our calculator called rand int to find pairs of students. We want to find pairs because we are drawing 2 students. So we want to find pairs of students. So on your calculator, if you hit the math button and then go over to PRB, which is probability, there is a function called rand int. It's the 5th one down. And we're going to put in our range of values. So our lower value is going to be 1. Our upper bound is going to be 95 because there are 95 students. And n is going to be 2 because we want to draw pairs of students. And then we're going to hit paste, and then we're going to hit enter. And it's going to give me 2 numbers randomly. The first 2 numbers it gives me are 45 and 46. So now I want to look to see if these 2 students are in stats. And neither of them are. And I want to repeat this a specific number of times, like 10 times, to see how many times both students are from stats. So I do it again, and I get 21 and 10. Both of those students are in stats. I do it again, I get 35 and 61, neither of which are in stats. And I can just keep hitting enter. We get 14 and 64. 14 is in stats, but 64 is not. Then we get 2 and 57. So 2 is in stats, but 57 is not. Then we get 27 and 2, both of which are in stats. Then 88 and 80, neither of which are in stats. 25 and 69, so 25 is in stats, but 69 is not. 24 and 10, both of which are in stats. And then lastly, 70 and 22. 70 is not in stats, but 22 is. So now I look and see, now I perform my conclusion. So looking in my simulation, of my 10 trials where I drew 2 students, in only 3 of my 10 cases were both students from stats, which is not a high percentage. So I can conclude, so is the lottery fair? I can conclude yes, because there is only a 30% chance that both students were from stats. So the students that thought the lottery had been rigged, it wasn't. So only a 30% chance that both of them had been from stats. So I guess we could say, is the lottery fair? Yes. In our second example, we have, in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of these NASCAR drivers: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. The company says that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of cereal until she has all 5 drivers' cards. She's surprised when it takes her 23 boxes to get the full set of cards. Should she be surprised? Design and carry out a simulation to help answer the question. So our question is going to be, is 23 boxes too much? Because she was surprised that it took 23 boxes to get the full set of cards. So my plan is to assign numbers to the 5 cards. So I can assign the number 1 to, I'm using initials here, Jeff Gordon, 2 to Dale Earnhardt Jr., 3 to Tony Stewart, 4 to Danica Patrick, and then 5 to Jimmy Johnson. Okay. And then we can use randint to find the number of boxes of cereal. So now for my do, I go back into math and over to probability, go down to randint. So my lower is going to be 1. This time my upper is only going to be 5 because I only have 5 numbers. And my n is going to be 1 because I'm going to draw one of them at a time. And I want to see how many trials it gets me to get the numbers 1 through 5 to appear. So my first trial, I got 5, which is one of my numbers. My second trial, I got 4. My third trial, I got 2. And my fourth trial, I got 2 again, which is a repeat, so it doesn't count. Then I got 5 again. And then 5 again. Then I got 1. Then I got 1 again. 4 again. 5 again. 4 again. 2 again. 1 again. 5 again. 1 again. 2 again. 1 again. Finally, I got 3. So in counting how many trials it took me, so if I count how many trials I have, it took me 18 trials to get all 5. So my conclusion is that no, she should not be surprised. Now, if you do this on your own, you may not have as many trials to get to all 5 cards. So your conclusion can be different based on how you actually carry out your simulation. So if you were able to get all 5 of them in 7 simulations instead of 18, then you would say, yes, she should be surprised, because it only took you 7 trials versus 18, or in her case, 23. So your conclusion doesn't necessarily have to match everyone if, because it's random which number you get out. And if I do this simulation again, it may take me fewer trials. It could take me more trials. It's just, that's why you repeatedly do simulations, so you can have, instead of just doing the simulation once. So please let me know if you have any questions over simulation.